Hey everybody, my name is Chris and I'm a tutor here at Chegg.com. I mostly do math and a little bit of computer science, and in this video we're going to talk about how to evaluate a double integral. So we want to evaluate the double integral where the region D is bounded by y equals x squared minus 1 and y equals x plus 1. So here we have the double integral over D of x times y dA, and remember dA just means dx dy, or it could be dy dx. It depends on the specific situation that you have. Alright, so the first thing that we really want to do is kind of get a picture of what's happening with this region D. So we know it's bounded by these two guys here. This is the standard parabola shifted down 1 unit, and this is just the line y equals x pushed up 1 unit. So before we draw a picture, let's go ahead and see where these two guys intersect. So how do we do that? Well, y equals x squared minus 1, y equals x plus 1. So what we can do is take x squared minus 1 and set it equal to x plus 1 and solve for x. And we can do that because both of those things equal y. So if we set them equal to each other, solve for x, that'll give us the x coordinates of the points of intersection. So in other words, what we want to do is say x squared minus 1 equals x plus 1, and then solve for x. So let's subtract x and subtract 1 from both sides, and then we get x squared minus x minus 2 equals 0. So this is a standard quadratic equation, and we can actually factor this and get x minus 2 times x plus 1 equals 0. So we get x equals 2 and negative 1. All right. Now, when x is 2, what's y? Well, since 2 and negative 1 are the values of x where these two intersect, we can actually use either of these to get the corresponding y coordinate. And this one will be much simpler because it's just x plus 1. So when x equals 2, we have y equals 3. And when x equals negative 1, we have y equals 0. So now we can use that to draw a picture, a more accurate picture of what's happening. So let's go ahead and do that. So here's our x-axis, here's our y-axis. So we have x squared minus 1. Now this doesn't have to be all nice and neat and perfect, we just kind of want to get a general feeling of what this region looks like. So here's y equals x squared minus 1, and then x plus 1, so remember it's going to intersect at negative 1 comma 0, and then 2 comma 3, which will be somewhere up here about. And then this here is our line, whoops, this here is our line, just pretend that's a straight line, y equals x plus 1. And then remember the region D is the region bounded by these two guys, so the region D is the shaded area in here. Okay, so we want to integrate over this region D the expression xy dA. So, well, we have bounds on x and bounds on y, right? So what we can say is negative 1 is less than or equal to x is less than or equal to 2. And we can actually use those as our bounds for x in the integral. What about the bounds on y? Now we might be tempted to say, well, hey, 0 is less than or equal to y is less than or equal to 3. And that's actually not true, because as we go through this region, we see that y actually becomes less than 0 down here, right? When y is in quadrant, or when we're integrating through the region and we get into quadrant 3 and 4, y is actually less than 0. So this is not always going to work. So what can we do to remedy that? Well, if we look closely at the region, we see that no matter what's going on with x, as long as we're between negative 1 and positive 2, we see that y is always between the line y equals x plus 1 and the parabola y equals x squared minus 1. And we also see that the line is always above the parabola. Okay? So then what we can say, actually, is x plus 1 what we should say is x squared minus 1 is less than or equal to y is less than or equal to x plus 1. So these are the bounds on y that we're going to put into the integral. Now you might be saying, well, hey, couldn't we have used 0 and 3 for y and then maybe use something else for the bounds on x? And in theory, yes. But if it's even possible in this case, it would have been much more complicated, much more messy, just something that we all around would like to avoid. So let's go ahead and convert this now into an integral with actual bounds. So the double integral over the region D of xy dA is going to be the integral. So which one do we put on the outside? Well, remember, when we evaluate double integrals like this, we always work from the inside out. So the outer integral needs to have the constant bounds, because our final answer in the very end should just be a number. So we want to make sure that the outer integral has the constant number bounds on it. So the integral from -1 to 2 of the integral from x squared minus 1 to x plus 1, we just have xy. And then dA in this case is going to be dy dx, because we integrate with respect to y first, and we know that because these are the bounds on the inner integral. So we're integrating with respect to y first. Okay, so let's go ahead and evaluate this. So remember, we work from the inside out, so we still have the integral from -1 to 2. Now we're going to integrate xy with respect to y. So basically we're just going to treat x as a constant. Okay, so we still just have an x right here, because it's just a constant multiple essentially. And then if we integrate y, that gives us 1/2 y squared. And we're evaluating from y equals x squared minus 1 to y equals x plus 1. And don't forget, we still have a dx out here. Okay, now we're going to have to go to the next page. So this is going to equal, I'll rewrite what we have just to make it easier to follow along. It's times 1/2 y squared from y equals x squared minus 1 to y equals x plus 1 dx is what we're still going to have. Okay, and let's go ahead and evaluate. So this is going to be, let's pull out the 1/2 also. 1/2 times the integral from -1 to 2 of x times, let's do this. So we're going to have x plus 1 quantity squared minus x squared minus 1 quantity squared, and then we still have a dx. Okay, so all we did was we basically simplified this. So this part that I just circled became this part here that I just circled. Okay, so just evaluating integrals as usual, and then we have equals 1/2 times the integral from -1 to 2 of x times what's happening in here. Well, x plus 1 quantity squared, that's x squared plus 2x plus 1, and then let's go ahead and fix that. And then here we have minus, that's going to be x to the 4th minus 2x squared plus 1, and then we still have dx out there. So then this is going to be 1/2 times the integral from -1 to 2 of, let's go ahead and simplify this all at once. So if we want to distribute the minus sign, then what we're going to have here is x squared blah 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 minus -2x squared, so that means x squared plus 2x squared, which is going to be 3x squared. Okay, so that takes care of the x squared and the minus 2x squared. And then we also have plus 2x, and there are no other x terms over here. Oh, sorry, we also forgot, don't forget the x out here. So we have x times all of that. And then, where were we in here? So we also have plus 2x, and then there are no corresponding x terms, so plus 2x. Okay, so that takes care of the plus 2x. Now we also have plus 1, blah blah blah, minus plus 1. So this is actually 1 minus 1, which turns out to be 0. So that's good. That takes care of those. And then finally we have minus x to the 4th. So we're just going to have minus x to the 4th here. And then dx. And again, don't forget about the x that's still out here. Okay, so now we can just distribute the x, and we end up with 1/2 times the integral from -1 to 2 of 3x cubed plus 2x squared minus x to the 5th, and then we've got a dx on all of that. So now let's go ahead and go to the next page, and again this is 1/2 times the integral from -1 to 2 of 3x cubed plus 2x squared minus x to the 5th, dx on all that. And now it's pretty much just a standard calculus 1 type integral, but with a lot of messy algebra. So this is 1/2 times 3/4 x to the 4th plus 2/3 x cubed minus 1/6 x to the 6th. And we're evaluating from x equals -1 to x equals 2. So that's going to be 1/2 times 3/4 times 2 to the 4th, and 2 to the 4th is 16. And then plus 2/3 times 2 cubed. 2 cubed is 8. And then we have minus 1/6 times 2 to the 6th, and 2 to the 6th is 64. And then we're subtracting and then evaluating at -1. So 3/4 times -1 to the 4th. Well, -1 to the 4th is just 1. Okay, so we're just going to have 3/4 times 1, which is just 3/4. And then we have plus 2/3 times -1 cubed. -1 cubed is -1. So 2/3 times -1. And then we have minus 1/6 times -1 to the 6th. -1 to the 6th is just 1. So we just have a minus 1/6. Close all of our parentheses. And then from here, it's just a lot of messy algebra. And in order to save time and everybody's sanity, we're just going to skip all those steps. So it's pretty much standard, straightforward algebra. Just a lot of getting common denominators, simplifying, and things like that. And the final answer is going to be 27/8. Okay, so this has been an example of evaluating a double integral over a general region, and I hope you found this video helpful, and thank you for watching.